I hope everyone got a good night's sleep and everyone's excited for this second iteration of the YRQG seminar series. It's a great pleasure to share this second moment where we are here together. I just want to make a few points of order before we go towards the talk itself. So I want to mention that we have just launched the website for the seminar series yesterday, which I will leave here on the chat for you to see. There you can find information regarding future talks. There's also some big green buttons that you can press that will take you to the mailing list, but also to your YouTube channel where you can see previous talks that we might have had. So of course, at this stage, we only have one previous talk from Martin Amon, and also where you can join Slack. So we are very happy about this launch. Please take a look if you feel so inclined. And then the second point is about the structure for today's talk. So in general, what we'll do is we will have 45 minutes of a talk by the speaker, and then 45 minutes of discussion, which we hope to be, an open discussion where everyone can participate. That's the whole point of this YRQG initiative, is that people feel not constrained by eventual, by the weight of more senior researchers. I will mention that, as you've heard now, the talk will be recorded. So the portion of the talk, those 45 minutes, will be recorded, and then we will stop the recording after the talk itself. So the discussion will not be recorded. Feel free to ask questions during the talk if you want, but keep in mind that those questions will be recorded because the talk itself will be recorded. Finally, as I mentioned before, on the website, we have the Slack channel, which you are also encouraged to use to just have a general discussion, either about the talk or about previous talks or about any topics that you might think of in the context of the seminar. And finally, I wish you have a lot of fun and that you enjoy this. Please keep your cameras on during the discussion if possible. I think that just creates a much better environment. Okay, so without further ado, let me just introduce Rishabh. So our speaker today, Rishabh, he is currently a master's student at Göttingen, writing his thesis in the general topic of resolving singularities. And his talk today will be about the general idea of extending classical solutions towards the singularity of the Big Bang. So Rishabh, please go ahead. You have our attention. If you can start.
Thank you. Thank you so much, and thank you for actually giving me a chance and giving the second talk in the series of talks. So without further ado, let me share my screen. I hope, can you see this or no?
We can see you. Yeah.
Okay, good enough. And are you able to see my cursor?
Also, yes.
Okay, good enough. Thank you. Thank you so much. So, okay, welcome to the talk. Today, I'm going to talk about something which is related to the singularities, and we will only focus on the classical aspects, classical physics, and we will try to slowly build it up to show that there are certain cases, certain situations where classical degrees of freedom can uniquely continued through the Big Bang singularity, or basically any time-like singularity. Big Bang being just a particular case in question. So before we start, let's look at the motivation. The motivation of the talk is as follows: that general relativity, we know that it admits singular solutions. And the conventional wisdom tells us that all the classical degrees of freedom, the evolution of it breaks down, and accordingly, there is a breakdown of predictability at the singularity. When you go back in time, for example, in this case, the Big Bang. What in this talk I'm going to do is to challenge this notion via taking a particular example of Bianchi universe. We will see what Bianchi universes are, and just giving the major overall idea. Bianchi universes are homogeneous universes, which are not necessarily isotropic. So homogeneous but anisotropic universes. And we will see then that when the gravity in such universes are coupled to stiff sources implies, for example, in this case, we will take a scalar field. Then the Einstein field equations actually reduce to a system of ordinary differential equations which satisfy a certain existence and uniqueness theorem in mathematics. Accordingly, even at the singularity. Accordingly, we will see that challenging the conventional wisdom that that Einstein's equations, the solutions to the Einstein's equations can actually be used to predict what happened at the singularity and even before it. Then the model that we are going to use is, like I said, homogeneous anisotropic cosmological model, Bianchi IX. Accordingly, the FRWL cosmological model becomes a subset of it, which is coupled to a scalar field. And the methodology that we will employ is something called the Adm formalism of general relativity. As I understand that some of you might not be aware of it, so what the plan is to build it slowly up to that point and try to highlight all the physical points as well as the crucial steps that underlies this whole set of calculations. So let's look at the whole overview. So in the introduction, I'm going to just tell you about, like, it will be just a brief introduction to general relativity, which I'm expecting like a lot of you will be knowing. Then we will look at the 3+1 decomposition of space-time, basically into the space plus time component, which is also like, and the focus will be on Adm formalism. Then there will be something called hypersurface deformation algebra, which can be seen as a different starting point for general relativity. You can take this as the assumption and then get to the Einstein's field equations. Then we will give a brief introduction to the homogeneous universes, in particular the Bianchi IX universe. And finally, in the fifth section, we will actually look at that how whatever we have studied in sections 2, 3, and 4 can combine together to have a unique solution continuing through the singularity. With this in mind, let's start with the introduction. We know that the Einstein-Hilbert action looks like it has two components, one for the pure gravity and one for the sources. And this is how it looks like. In the case of just the pure vacuum case, there will be no matter sources. And then for the pure gravity, if we include only the pure gravity case, or if you take the whole Lagrangian and vary that Lagrangian or the action and put it to 0, then basically you will see that you get the Einstein's field equation. This is something which is, and the stress energy momentum tensor that you get is conserved. But this is the Lagrangian formulation of general relativity. What we are interested in this doing is that the Hamiltonian version of the general relativity, which requires that time and space be separate variables. Now, it is important to be said that in general relativity, time is not unique. It depends on your time parameterization, and time can be defined in different ways. So accordingly, this whole separation of time and space is not very clear, and it's a bit vague in that sense. So how do we get to the Hamiltonian? For that, we need to construct a setup of hypersurfaces. Let's look at what that means, and I'll try to give some images to have a mental picture in mind. So let's look at the 3+1 decomposition, where 3 implies the hypersurface, the spatial surfaces, and the 1 is the time dimension. Accordingly, let's look at what does it mean. So now this whole thing that you see, the whole bigger box that it is like the whole of space-time. You can imagine that to be the manifold M, the whole of space-time. What I'm trying to do is I'm trying to divide the space-time into layers of hypersurfaces. Accordingly, each of the layers will be a spatial surface, and the line joining them will be a time direction. And as you go up, it will be going up in time. And each of the slices that you cut through, these are completely spatial in nature. So with like, this is the hypersurface, and this is the embedding that we are going to deal with. But it's always good to have a mental image that what can we imagine. So this is what we will imagine. That suppose that we have a space-time M, which has a particular metric G mu nu. We are going to slice it into spatial foliations. Basically, sigma t are the hypersurfaces, as you can see in this diagram. So example, this sigma t is this, and then t plus delta t is just next hypersurface. So we are going to shear off the space-time into layers of hypersurfaces such that their union constitutes the whole space-time. Of course, you need to realize that there are no overlapping between any two hypersurfaces given. This is the starting assumption. Mathematically speaking, this can be done because we always assume space-time to be globally hyperbolic. If you have a globally hyperbolic space-time, this can always be done. This can be proved. And this is an assumption that always goes in the Hamiltonian approach to general relativity. Accordingly, now we are interested in the induced metric. What does that mean? Like, this means that G mu nu was the metric for the whole space-time, but on each of the spatial surface, you need to measure the distance between 2 points, right? That is given by this gamma mu nu metric. This is just the metric induced on the spatial hypersurface due to the whole space-time when you divide it. Accordingly, we realize that the G mu nu, the full metric, defines us the affine connection. Basically, like delta mu times G mu nu has to be 0. This gives us the definition of the covariant derivative, if you will. Accordingly, the gamma mu nu that is defined through this equation, where n mu and n nu are simply, like n mu is simply the normal vector to each of the hypersurface, then there is a corresponding definition of the affine connections on each of the hypersurface as well, which I will denote as d mu. So accordingly, the relation will be d mu times gamma mu nu will be 0. And of course, the inverse metric can be defined similarly on this graph. But induced metric is not the only ingredient that you will require, because the moment you start separating into space and time, you are also interested in knowing that how the curvature changes from one hypersurface to another hypersurface. So you are interested in the curvature of the hypersurface, which is something intrinsic to one hypersurface, but you are also interested in that how that changes as you go from one hypersurface to another. That leads to two new concepts. The intrinsic curvature, just like in 4 dimension, the G mu nu led to Ricci scalar. Accordingly, the gamma mu nu will lead to a 3 scalar. That will just tell you about the curvature on the hypersurface, one hypersurface. But that is not enough. One more ingredient is required, and that is the extrinsic curvature. That will tell you that what will be the gradient between as you go from one hypersurface to another. And that is defined using this definition. This can be, in fact, taken to be the definition. There are other definitions, starting points of this as well, but I'm choosing to go with this one. Accordingly, K mu nu is the extrinsic curvature tensor, and just like you define Ricci tensor scalar, you can define an extrinsic curvature scalar. This completely defines. So in 4-dimensional space-time, all you required was G mu nu, and that used to lead to everything. That used to define the curvature tensor and everything. In the 3+1 formulation, you need an induced metric that is given in terms of this, an intrinsic curvature that will define the curvature on one hypersurface, and the extrinsic curvature that will tell you that how the curvature changes. So accordingly, the bottom three points is same as having a full space-time with a metric G mu nu. With this ingredient, let's go forward and define something. Let's focus on 2 hypersurfaces, just 2. For example, in this diagram, you can just see that sigma t and sigma t plus dt. So just focus on these 2 hypersurfaces. Accordingly, there are 2 functions that have got significant physical intuition that whenever, if you will read the Hamiltonian decomposition, you will always get to know about it. The first is the n. This is the lapse function. What does it do? Let's focus on the diagram. Like suppose that A and C, if you go along a time direction that you have defined, then you go to C. But if you go along the normal, the n mu direction, you reach at B. Accordingly, the lapse function tells you the difference between the actual time trajectory and the one that you take towards going perpendicular to a hypersurface. And what does this NA is the shift function. That measures that when you reach the next hypersurface, what is the spatial distance between these 2 points that you are getting at. These 2 are one of the key ingredients in the Adm formalism, and they are defined as follows. This whole metric, the metric that we take, the G mu nu, when you take this decomposition, can be written in terms of the Ni, the shift functions, and the N, the lapse function, and it can be decomposed like this. Here, the gamma ij is the same one that we introduced in the last notation, where mu nu can take the ij indices, the spatial indices. So accordingly, the metric gets broken down into this, where the first component is the 0,0th component, the nj and ni are the 0i and the i0 components, and the gamma ij is the spatial component of the metric. Accordingly, the inverse metric can be shown to be equated to this. Accordingly, now what do we have at hand? We have induced metric gamma ij that can be read off from this. We have extrinsic curvature, intrinsic curvature, and the metric can be decomposed using the lapse and the shift functions. This is the whole thing, and this completely constitutes what we will require in this talk. The normal vector can further be written in terms of the lapse functions, and the time evolution vector, the t mu that you see here, can be written as a combination of the lapse plus the shift function. With this in mind, we have finally covered the basics of it. If you have any, I hope I am trying to give you the physical interpretation of the lapse and the shift, and a mental image to take it with you. If this is clear, then we go to what the missing ingredient is. I don't want you to look at the equation because this looks like horrendous, but it has to be put there. But the idea of putting it is to tell you that even if you have all the relations in the 3+1 decomposition, in the foliation of space-time, there are few relations, mathematical relations, that you will need to project the full Einstein field equations into the space and the time component. What are those missing ingredients? All I want you to focus on the LHS and the RHS that I'm going to follow. Otherwise, this formula is just horribly bad. As you see that all the LHS thing that you see, these are the four components, the four space-time components. And on the RHS, it is completely broken down into three components, where R3 is the three scalar, Ricci scalar, for example. The K is like the extrinsic curvature. The Kij is the extrinsic curvature tensor. So there's something called Gauss, Kodazzi, and Mainardi relations that allow you to decompose a four-dimensional quantities in the full space-time to the 3+1 quantities that are given on each of the RHS of each of these relations. This is the final missing ingredient apart from what we discussed right now. When you take these things in, you get as follows. Now, let's follow a line. Let's follow an observer whose velocity is time-like, the n alpha. Or if you want to have a mental picture, for example, the n alpha is the perpendicular direction from one hypersurface to another. So let's consider a frame of reference in which an observer is moving with a time-like velocity, n alpha. So basically from one hypersurface to another hypersurface. This is the frame of reference that we are going to take. Now, the moment you take it, you realize that on the right-hand side of the Einstein field equation, what did you have? You had the stress-energy tensor. So now, stress-energy tensor, mathematically, there are three possibilities that you take to projections, both along the normal, one along the normal and the hypersurface, and both along the hypersurfaces. These are the three possibilities, and that's what it is shown here. That when you take the T mu nu, you project both along the normal. Basically, then that projection just means that multiply with n nu, you get something called energy density. If you project one component along the normal, basically the n mu here, and one along the hypersurface by multiplying with the 3 metric, this minus sign is conventional, then you get something called momentum density. These are just standard terminologies. And if you project both along the spatial hypersurface, basically simply by contracting it with the 3 metric, you get the stress tensor. Now, accordingly, we can see that these three are not completely independent. There is a relation that exists between this. T is the self-contracted stress tensor in the full space-time, and S is just along the sigma T, and this is the relation that is satisfied. But the point is that the stress energy momentum tensor can be broken down into three parts, depending on your projection. Once we have taken the projection of the RHS of the Einstein's field equations, let's start looking at the LHS of the field equation. We realize that, of course, again, just like the energy momentum tensor, Einstein field equations will have three types. You can take the projections basically in three ways. Again, you either project both the components along the normal, you project one along the normal, one along the hypersurface, or you project both along the hypersurface. The right-hand side has already been defined using the point number 2 here. And so the E, P alpha, and in the last point, the S alpha beta, these are just the projections of the energy momentum tensor. But the LHS is something which if you remember the Einstein's field equation, that if you start projecting using the Gauss-Kodazzi Mainardi relation, these are the LHS that you will get. If the only crucial point to understand is that if you project both along the normal, it's like projecting along the time-like hypersurface, time-like curve. That is what is called Hamiltonian Constraint. So when you project the Einstein's field equation twice along the time-like hypersurfaces, time-like curves, accordingly, that is called Hamiltonian Constraint. If you project the Einstein field equation one along the normal and one on the spatial hypersurface itself, that is the momentum constraint. The last one is to show you that this is how it looks if you project the Einstein field equation on one hypersurface, just one hypersurface. Accordingly, we have projected the Einstein's field equations in terms of this, in terms of the 3+1 composition. And what we are going to do is we are going to look at the Hamiltonian corresponding to these set of equations, basically find a Hamiltonian that will lead us to this Einstein's field equations as well. So let's look at the Adm formalism for this. We started with the Hilbert action term, which was simply this, where R is just the Ricci-Curvature scalar. We realize that this 4, now let's start decomposing each of the terms separately. The d4x will simply become d3x times dt. So integration over the space and time. Then you realize that this thing, this whole 4R thing can be decomposed into using again the relations that this can be decomposed like this in terms of the 3 quantities that we have on the hypersurface, and the metric, the measure of, can be decomposed into the lapse function times the determinant of the metric. With this decomposition, when you plug it back in, you will get this as the this as the action. This is called the ADM action, where we have taken a crucial assumption that all the boundary terms we are excluding. We are not considering any boundary terms. We are just looking at the bulk of the space-time. If you will just ignore all the boundary terms and rearrange these things, you will get some total divergences. I will just ignore them, and this is what you are left with. This is the ADM action, and this is the ADM Lagrangian. So n root gamma is simply this root of minus g, and the rest is just the bulk term of the 4 Ricci scalar. We have got the Lagrangian here. Now, once you got the Lagrangian, the next step is, just like classical mechanics, we need to start calculating the conjugate momenta so that we get to the Hamiltonian. Then accordingly, what are the conjugate momenta? There are 4 dynamical variables, like in this case, like we are taking the 3 cases that we are taking, the n, the ni, and the metric itself. These are the 3 so-called dynamical terms. We will see that not all of them are dynamical, but the point is that these are the 3 dynamical terms corresponding to which we can define the momenta. Just using from typical analytical mechanics course, we define the conjugate momenta. We realize that there is no n dot appearing here. There is no ni dot appearing here. So accordingly, the conjugate momenta corresponding to the lapse and the shift functions are 0. And then, of course, the pi ij is with respect to the pi ij is the metric momenta corresponding to this metric. And this is what you get. Now, these are the conjugate momenta you have obtained. Then what will be the Hamiltonian? Again, from the classical mechanics, we know that the Hamiltonian density will be, there will be 2 more terms here that would have been pi n times n dot plus pi ni times ni dot plus this term minus L. But since these 2 are 0, so those 2 terms can be taken to be 0. And this is the Hamiltonian density that you will get. So starting from the Lagrangian, what we did, just as a quick recap, we wrote down the Einstein-Hilbert action. We knew the Lagrangian. We foliated the space-time into space plus time. We used Gauss relations to project the Einstein's field equations. And now we are projecting the Hilbert action term to get the Lagrangian of the ADM. And then from there, we calculated the conjugate momenta to get the Hamiltonian density. When you will plug everything in, always remember that we are never including the boundary terms. So once you will plug it in, you will get something. It can be taken to be 2 separate things. The full Hamiltonian of the Adm formalism will depend on 2 components. One will be on the lapse function and one will be on the shift function, n vector or ni. Accordingly, the Hamiltonian constant, the first term is called the Hamiltonian constant. It will look something like this. Crucial point is that it depends on, it is proportional to n. And the diffeomorphism constant will be this term. So accordingly, when you, let me go back, when you finally plug everything in this here, you will get something of this form. Now, the ADM action then accordingly will become this. Basically, this is just now we saw that this is equated to the Lagrangian of the ADM. Now, the restriction that we have is that on the boundary of each hypersurface, we will not allow the n, the lapse function, the shift functions, and the metric not to vary at the boundary. You will see that there is no restriction put on the conjugate momenta pi ij. It is free to evolve, even it is free to take any value on the boundary, but the shift, the lapse, and the 3 metric has to be 0, has to go to 0 on the boundary of each of the hypersurfaces. These are the restrictions, and this is how you obtain the Adm formalism of general relativity. Now we have got the Hamiltonian, we have got the Hamiltonian constraint and the diffeomorphism constraint. Let's go and look at the equations of motion. The moment we have the Hamiltonian, let's start focusing on the equations of motion. The first is, okay, again, we have realized that n and ni, and of course the gamma metric, these are the 3 things that we took when we were calculating the conjugate momenta. So the first equation of motion will be by varying the lapse function and the shift functions. When you will vary that, you will realize that the Hamiltonian constant and the diffeomorphism constant that we wrote for the bulk term is actually equal to 0. What does this mean? This means that the n and the ni that appeared here in the Hamiltonian, the n and the ni that appeared in the Hamiltonian, these are Lagrange multipliers. To give a basic idea, suppose what are Lagrange multipliers used for? They are used for optimization, constrained optimization problems. For example, if you need to optimize a function f, given that g equals 0, what do? You create a new function f plus lambda g, and then you try to optimize that, given under the constraint of g equals 0. Similarly, the h and d becomes identically 0. Accordingly, any prefactor that multiplies these things are a Lagrange multiplier. So this tells a very crucial thing, that when we were calculating the conjugate momenta for corresponding to n, ni, and gamma ij, n and ni are not dynamical degrees of freedom. These are just Lagrange multipliers. So the only dynamical variables that we have in the 3+1 decomposition is the 3 metric. Accordingly, let's calculate the equations of motion corresponding to the 3 metric. Equations of motion corresponding to the 3 metric will be like this. You have to take this to be 0. Accordingly, the gamma ij, this is how the gamma ij will evolve in time, and this is the definition of, this is the equation of motion of evolution of gamma ij. To give an idea, and of course, when you vary with respect to the gamma ij, to give you an idea, it looks very complicated what is about to come. But for completeness, I have to show that similarly that you can start calculating the evolution equations corresponding to the pi ij. It looks something like this, not at all pretty, but this is what it is. So the point is that what we got, we got the Hamiltonian of the full general relativity in terms of ADM variables, like the shift and the lapse functions. We calculated the equations of motion. We realized that nis are just constraint equations. These are Lagrange multipliers. And the Hamilton's equations of motion are two. One will tell you the time evolution of the metric itself, and another will tell you the time evolution of the conjugate momentum of the metric. So with this thing, let's look at something called hypersurface deformation algebra. What I will do is I will go back to this picture where the ADM Hamiltonian is actually divided into two components, the Hamiltonian constraint and the diffeomorphism constraint. This looks all pretty mathematical, of course it is, but there is a very nice physical interpretation of this Hamiltonian constraint and the diffeomorphism constraint. If nothing, if this mental image that you take here in the next slide, that will be enough. The idea is that the Poisson bracket of these two on any constraint surface means any hypersurface, any spatial hypersurface, will vanish. Accordingly, not vanish, but it will form a closed algebra. These are the Poisson equation looks like. When you take two diffeomorphism constraints, you will end up with a diffeomorphism constraint. One diffeomorphism, one Hamiltonian will form a Hamiltonian constraint, and Hamiltonian will form another diffeomorphism constraint. Point is that this algebra is closed. And this is also called something called the Dirac algebra. This can be taken as the starting point of general relativity, and you can actually go on to derive the Einstein-Searle equation from this algebra itself. But what does this physically mean? What does this mean that the algebra is closed? Let's look at that. Of course, one intermediate point, that this hypersurface deformation algebra, if you take the Minkowski limit, basically the gamma jk, if you take this to be simply eta mu nu or eta ij, it will reduce to the standard Poincaré algebra. So the hypersurface deformation algebra is a generalization of the Poincaré algebra in the full spacetime metric. The physical meaning is as follows. Let's look at the A part, where there are two diffeomorphism constraints that lead to another diffeomorphism constraint. Physically, it means that if you take just one hypersurface, just focus on one hypersurface, you go, suppose that, like, of course, because we are calculating the Poisson bracket, if you go, say, chi-i direction first and then the psi-i direction, or you first go the psi-i direction and then the chi-j direction, they will not meet at the endpoints. It depends on which direction you are traveling first. There will be a gap as shown in red. That red is exactly what the RHS denote. So whatever remain, that if you take these two if you do these two transformations, at the end of it, this red one is again a diffeomorphism constraint. So this is what it means to be closed. Now, again, look at the diffeomorphism constraint. Diffeomorphism constraint will take you from one point to another on the hypersurface. Hamiltonian constraint will take you from one hypersurface to another hypersurface. So in the second case, suppose that for the B part, you take a diffeomorphism constraint, you translate chi-i, then Hamiltonian constraint takes you to phi. Or you first take the Hamiltonian constraint phi and then take a diffeomorphism constraint that takes you chi in the direction. The final gap they will not necessarily meet. But you see that in this case, the direction is time-like because it's not lying on the hypersurface. That intermediate gap is given by the right-hand side of the Hamiltonian constraint. That's why it's a Hamiltonian constraint, because it takes you in the time-like direction. Similarly, for the final part, if you again have two hypersurfaces, first you take sigma Hamiltonian, then phi, or you take phi and sigma. These dotted lines are just some pseudo spaces. Accordingly, you will realize that both of them will lead to two different points on the same hypersurface sigma 2. And again, as you see that these two are on the same hypersurface, the right-hand side should be a diffeomorphism, which it is. So this is the physical image of the Hamiltonian constraints and the diffeomorphism constraints. Diffeomorphism constraints take you from one point to another on the same hypersurface. Hamiltonian constraints take you from one hypersurface to the next. I hope that this is what like the physical picture is clear, because this is what it means of writing the Adm Hamiltonian here. This is what the physical picture means in terms of the hypersurfaces that we saw in the previous sections. So now with this thing in mind, like the hypersurface deformation algebra, we have covered one part of continuing through the Big Bang solution, the one of the prerequisite, that is the Adm formalism. And I have tried to give you the mental picture for the shift function, the lapse function, and the Hamiltonian constraint and diffeomorphism constraints. That part is done. Let's look at the second part of the talk, which is the homogeneous universes, which will be our playground to show that the solutions can be uniquely extended through the singularity. So what are homogeneous universes? Let's look at that. That homogeneous universes means, like, we are considering now a hypersurface which is homogeneous at each point, but it cannot be isotropic. It may need not to be isotropic. What does this mean? This means that there are three-dimensional linearly independent killing vector fields on each of the at each point on the hypersurface, because you have homogeneity at each of the points. So accordingly, and it's a three-dimensional homogeneity. So accordingly, there will be three-dimensional linearly independent killing vectors at each point on the hypersurface sigma t. And you realize that the isometric group of the manifold form a closed Lie algebra, that if I take all the killing vector fields, they will form a closed Lie algebra. The Lie algebra of the killing vector fields will look like this, where the xi A and xi B are simply the killing vector fields at each point on each of the hypersurfaces. When you take their commutation relation, this will be equal to this, where the C is some structure constant of the algebra. Why am I doing this? Because I'm trying to show you that this is how the Bianchi classified originally the homogeneous universe, that even just by starting from the condition of homogeneity, you can reduce that, okay, there must be some killing vectors that must form a closed algebra, and you should be able to write this. Basically, having a homogeneous space implies equation number 5. It's as simple, it's like that. It's the mathematical translation of saying it in English. So then this C, the structure constant, allows us to classify various types of homogeneous universes. Unlike the FRWL, where there is only one possibility of having a homogeneous and isotropy, in homogeneous universes, there are multiple possibilities, and we are going to look at that. The structure constants of this Lie algebra satisfies these two relations, which can be again shown that for the homogeneous, it should hold. Now, what we do is, using the Levi-Civita symbol, we define another matrix C delta gamma. This can be shown that this matrix C delta gamma that is written here can be, in the most general form for a homogeneous universe, can be written like this. It can be written like this variable. Now, as you can see, there can be various possibilities that the values of n1, n2, n3, and a can take. These can be either 0 or 1, and there can be a lot of possibilities that actually lead to a wide variety of classifications: Bianchi 1, Bianchi 2, Bianchi 3, Bianchi 4, like that. What we are interested is in the Bianchi IX universe that we are going to talk about, which is just another fancy way of just saying that these a, n1, n2, and n3 will take these values. So when you take these values, this becomes a diagonal matrix, and this diagonal matrix C alpha beta will define a particular this 3 tensor, and that will define this particular thing. So accordingly, when you go back and plug it back everything in here, then this Lie algebra will correspond to the Bianchi IX universe. Now, with this thing, let's focus on the Bianchi IX universe itself. there I just wanted to show you that why there is not just one homogeneous universe, but multiple homogeneous universes, unlike the FRWL case, where there's just one possibility. So then, accordingly, the Bianchi IX is actually topologically similar to the SU2, which we know that SU2 is topologically similar to a three-sphere, and it looks like this. In the Bianchi IX, when you plug everything back in, like going one step back, like I said, the structure constant will turn out to be the structure constant will turn out to be a Levi-Civita thing. Now we realize that the Bianchi IX can be entirely mapped onto a three-sphere. On the three-sphere, we have the hyperspherical coordinates just like a normal two-sphere. These are the hyperspherical coordinates that can be written in terms of the r, theta, and phi. And these are the four coordinates. Of course, this should satisfy this relation, 1. That the radius of this hyperspherical coordinate is 1. And accordingly, the Bianchi IX can be mapped onto this sphere, where r theta is standard 0 to pi and phi is from 0 to 2 pi. These are the spherical coordinates of the three-sphere. This mapping to the three-sphere will be very crucial for us when we will try to map the solutions onto the sphere. Now, what does this mean? Like where does this go? Now, there's something called gauge fixing and solving diffeomorphism constant. Let's pause for a moment and realize we had, when we divided the Hamiltonian into the Hamilton constant and the diffeomorphism constant, and we wrote down the Adm Hamiltonian, we realized that the Hamiltonian constraint as well as the diffeomorphism constant should be individually 0. Let me quickly go back to that thing here. We realized that when we were calculating the equations of motion, that in the Adm Hamiltonian h plus d, these are 0 on each of the hypersurfaces that we are considering. Accordingly, let's move forward. What you can do is, like, when you solve the Hamiltonian constraints and the diffeomorphism constraint, basically, you put d equals 0, you solve for the metric, and you h equals 0, you solve for the metric. The diffeomorphism constant has 3 components, so that will give you 3 equations, and the Hamiltonian equals to 0 is 1. Point is that after you solve those 2 constraint relations, those 2 constraint equations, and you do a certain gauge fixing, you lead to in something in the literature which is called Ashtekar-Henderson-Sloan variables. And point is that for Bianchi IX, if you solve it, you will be able to show that the 3 metric on each of the hypersurfaces that we solve is a diagonal metric. And we realize that the commutation between the gamma and pi has to be 0. Accordingly, the pi ij is also a diagonal metric. Accordingly, for the Adm formalism for Bianchi IX will lead you to diagonal metric for gamma ij and the pi ij. This is crucial. Now, once you have written this, it can be shown that the gamma ij, it is metric, but now you need to solve for the q1, q2, and q3, which are the AHS variables. Once you will solve for it, you will get something like this. What is it? Let's talk about the physical meaning of it. If you put x, y, and z as x and y as 0, you will get a standard, the Minkowski, like the kind of an FRWL kind of a structure, where all the diagonal terms will be 0, because if you remember the FRWL, it is something like dt square minus a square dx square. Accordingly, this x and y that you see, these are the measures of anisotropy. How much of the Bianchi IX is not isotropic? This is measured by x and y. Accordingly, when x equals y equals 0, you will get the FRWL universe out of the Bianchi IX. So this x and y are called the Misner variables that measure the anisotropy of a homogeneous universe. And when you put x equals 0 and y equals 0, you will get back the FRWL universe. So FRWL is a subset of it. This V is simply the 3 volume on each of the hypersurface. Now, under these variables, the Hamiltonian constraint will look like this. The first 2, these terms are like standard, like you can imagine like a free particle moving, kx square plus ky square, and there's a time square term, times certain potential. The potential looks like this. As you can imagine, can you try to imagine that this is like a triangular shaped curved billiards ball table. This is the mental image that at least I have when I think of it. Why? I'll tell you why. This is how the potential looks like. Let me go to the next slide and then I will tell you why. Point is that once you have got this Hamiltonian constraint, you can start calculating the equations of motion. And the equations of motion, this equation you ignore for now, look at this graph because that is what it is plotted. You will see that when you will plot it, the volume will be 0 at the very past and at the very future. What does this tell you? That there are two singularities that happen in a Bianchi IX universe, one in the extreme past, one in the extreme future, because that is the only variable that we have. How do we define singularity where one dimension further collapses and the volume goes to 0? In this case, because we are not considering right now any matter sources, we are just looking at the vacuum case of the Bianchi IX. Accordingly, in the Bianchi IX, we realize that V tends to 0 is a singularity, which it can be shown that when Misner variables diverge, any one of them diverge, not both. This is the same as having a Bianchi, this is the same as having a singularity there. So in terms, that's why now I hope like I'm able to convince that Misner variables are really useful apart from just measuring the anisotropy, because they also tell you where the singularity lies. And then accordingly, let's look at the certain solutions, and then let's go back to that graph that we were talking about, which looks like a Billiard table.
Excuse me?
Yes.
Could you say what tau and kxy were?
Okay, yes. Yeah. This kx and ky are the conjugate variables corresponding to the x and y. These are the conjugate variables that you corresponding to the x and y, conjugate momenta, you can call it. The volume is the standard 3 volume, and this tau is the conjugate momenta corresponding to this 3 volume, which is also called York time. Thank you for the question. Actually, this I should have said that the kx, ky are the conjugate momenta corresponding to x and y. The tau is the conjugate momenta corresponding to the 3 volume.
Okay.
And, yeah. Thank you for the question, actually. So then accordingly, let's proceed and let's look at the compactification of the configuration space. Let's look at this diagram. Just look at this diagram and let's start talking about it. What in general relativity, we know that general relativity is completely blind to the orientation of the manifold. We know that a manifold will matter, but like even if you have a manifold that goes like this or the other way around, general relativity will not differentiate between the two manifolds of the space-time, two orientations of the space-time. Accordingly, when we are considering in terms of the Bianchi IX or the Adm formalism, we need to include, in this case, both the orientations of the manifolds that we are talking about. There are two possibilities of the orientations in the 2-dimension, in the 3-dimension that we are talking. And this is how it looks. The upper plane, the one in the green, is corresponding to one manifold, one orientation of the manifold, and the bottom one corresponds to another orientation of the manifold. General relativity, remember, they will not distinguish between these two types. So we have to take both into account. The type of topology that I'm choosing is that I'm gluing both of the hemispheres at the equator, and I'm gluing them together. This is the configuration space that we are talking about. Now, this is just to give you a mental image that this will be our playing ground, because we also know that the Bianchi IX can be mapped onto a 3-sphere. This is the case of a 2-sphere because it's difficult to draw a 3-sphere here and to give you the intuition for that. So for the case of a 2-sphere, this is how it will look like. We will do a similar thing corresponding to a 3-sphere because Bianchi IX can be topologically mapped to a 3-sphere. Accordingly, these are the coordinates. We all know that these are the coordinates. And you can see that the x and y, these are the Misner variables. So x and y can be mapped on to the spherical coordinates alpha and beta. Similarly, the x1, x2, x3 can also be like the coordinates on the sphere can be mapped in terms of the alpha and beta. This is what we, because we have already written, once again, we have already written the Misner variables in terms of x and y. We need to find a way to map it onto the 3-sphere. Why it is important, we will see that. Let's look at one of the orientation. Let's focus on one of the orientation. Suppose that this is one of the sphere, one of the orientation of the manifold. This blue line that you can see, it's like a geodesic, a particle moving freely. What does that correspond to on the sphere? It will correspond to a semicircle, a great semicircle on the sphere. Similarly, corresponding to the other orientation, on the other orientation, suppose if this is the geodesic, it will get projected to the another great semicircle on the sphere. This is what the projection we are talking about. That if this is the Misner plane, xy, top and bottom, the flat planes, which are at the north pole and the south pole of this equator, if you will start projecting them, the geodesics will start looking like the semicircles, the giant semicircles passing through the passing through this point. Like here, the top one will start from this point at the equator and will go to the other point at the equator, and similarly, the green one will be on the bottom hemisphere. Point is that there are two poles, because when we were mapping this thing, when we were mapping the x and y Misner variables, I hope you remember that the Misner variables diverging shows you singularity. And when we were talking about this mnemonic projection, you see that when will x and y diverge? When beta tends to pi by 2. If beta tends to pi by 2, and x and y will both diverge. So this gives us the first concrete definition, or like the point on this sphere, that where does the singularity lie? That beta equals 0 and pi, x and y are 0. So where is beta 0? At the north pole. Where is beta pi? At the south pole. So in this spherical projection, the north pole and the south pole are the FRWL universe. But when beta tends to pi by 2, x and y tends to infinity, accordingly volume tends to 0, and the equator of this great sphere is the singularity, which is what we are going to focus. So why is this mnemonic projection so useful? Because it allows us to capture singularity on a limited, in a very compact way on a sphere. So now we realize that the top and the north one are FRWL and the equator is the singularity itself. What about the color plots? These color plots are what we are about to come next. The potential that we saw way back, which looked like a triangular shaped billiards table, like you can imagine. So that the redder one is like where the potential is very high. The blue ones are where the potential is very low. But let's look at that. That we have been able to project the equator, the FRWL and the singularity on it. Now let's consider now let's go back to that potential. If you do, imagine these are the triangular projections. This exactly let me quickly go back. This is if you start imagining from the top view, if you start plotting it, a two-dimensional plot of it. This is how it will look like. As you can see, these can be imagined like a billiard ball in a triangular pool table. These potentials u, x, and y, that the potential that you had, with time, they are going away. It is expanding. The walls of that potential is moving out and out and out and out. So if you take the simulation that is done here, the numerical simulation, point is that imagine a ball, a particle in that space. It is going in one direction, moving freely, till it hits one of the walls of the boundary, one of the walls of the potential. It scatters, takes a new free path, till it hits another wall of the potential. Then again it scatters, it will go again. Now, you can always ask that the walls of the potential is receding very fast. So is it possible that the walls of the potential will recede so fast that the particles will never be able to reach that? So if that happens, if the walls recede so fast that the particles will never be able to touch it, then the final path of the particle will be just like a free particle, never scattering again. But in pure Bianchi, potential walls will never run away sufficiently fast that the particle never catches up with them. So if I just take the pure Bianchi IX universe, it is never possible that the particles will not be able to reach it. Particle will always reach it, and till x and y tends to infinity, basically till the singularity, the particle will keep constantly scattering off. This is what Misner famously called the perfect scrambler of nature. That if you have started with a particle at the initial condition, given it some initial condition, and let the particle evolve towards the singularity, no information will be saved of that initial condition because of the infinite bounces that will happen before the particle reaches the singularity. In a way, this is what Misner was meaning when he was talking about the perfect scrambler, that classical physics break down at the singularity because no information of the initial condition will be saved when the particle reaches that infinite point and that singular point. Accordingly, the point is that is there a particular coupling that we can find with pure Bianchi IX that will allow the walls to recede so fast that the particle will finally set on a free motion, a straight motion, and will never be able to reach the box, will never be able to reach the walls of the potential, even when it reaches the singularity. If that can be shown, accordingly, you can say that some information of the initial condition can be sustained at the singularity. And this is what the physical picture of this whole means. Accordingly, as singularity is reached, any information about initial condition will be erased due to infinite bounces in finite proper time, because the particle will reach the singularity in a finite proper time, but there will be infinite bounces in between. That is what is called perfect scrambler. But if we are able to show that there are not infinite bounces, and the particle will reach singularity in a finite number of bounces because the walls of the potential will recede very fast, then that solution can be extended through the singularity. Let's look at if it can be done or not. Let's consider.
Rishabh, sorry to interrupt. Quick notice: the 45 minutes are over, so please try to conclude soon.
Yeah. Okay. Yes, I will. So accordingly, it's like just thank you for the notification. Actually, but yes, like it will just take me 5 more minutes. So now we will consider the simplest example of free and massless scalar field. Let's look again. Write down the ADM action. This time, the terms written in the greens are the new contributions corresponding to the scalar field phi. Everything is same, so it is Bianchi IX plus the scalar components. This is what you will get for the Hamiltonian diffeomorphism constraint. You redo the whole step, again, solve the diffeomorphism constraint, use the AHS variables to write down the metric and everything. You write it in terms of the Misner variables x, y, v. And once you have written it down, this is the final Hamiltonian that you will get, which has a very clear physical interpretation. This one is just like a Minkowski free particle, the first term, and second term is like a potential. So this is what you will get if you couple the Bianchi IX to a scalar field. Again, go to the mnemonic projection, project it on a sphere, and then the final Hamiltonian that you will get is this form. Point is that, again, there are a series of change of variables, but the point is that the idea is the same. You again write down the action, you write down find the Hamiltonian constraint when gravity is coupled to the Bianchi IX, to the scalar field. You take a mnemonic projection, and this is what the Hamiltonian looks like. Once you have got the Hamiltonian, remember this all started from the Einstein's field equations, the Einstein-Hilbert action. You write down the equations of motion. The equations of motion turns out to be the simple ordinary differential equations. These are the ODEs that you will get, and these satisfy in the after the slide, I have another slide, a backup slide I will show you. These are completely regular when beta tends to pi by 2. If you will put the beta tends to pi by 2, this is finite. Nothing blows up. This set of ordinary differential equation, but it goes deeper than that. The right-hand side, these ODEs satisfy something called Picard-Lindelof existence and uniqueness theorem. What it is, we can talk about after the talk, but it satisfies this particular existence and uniqueness theorem at the singularity. So accordingly, not just the solutions will exist, but they can uniquely be traveled across the equator in that 3-sphere picture. And it actually goes more than that. Even the first derivatives, if you take another derivative of these equations with respect to the 8 pair of conjugate variables, like the L, theta, and such things, the first derivative of these ODEs are also regular when beta tends to pi by 2. So it just not satisfy the Picard-Lindelof existence and uniqueness theorem. It goes beyond that, and the first derivative also satisfies it. So it's completely differentiable. And this is how you actually extend the solutions beyond the singularity by taking this particular case. The idea is that Adm formalism allows you to separate time and space variables and thus write the Hamiltonian general relativity. Then we looked at the Bianchi IX universe and saw that pure Bianchi IX is unable to allow classical physics to survive at the singularity due to infinite collisions. But when coupled to scalar field, they lead to a set of ordinary differential equations which satisfy Picard-Lindelof. Accordingly, the coupling scalar field in the presence of a potential. This has also been shown. We talked about the free and massless scalar field. But if you would have taken a scalar field in a potential, that has also been shown and published, in fact, to survive through the singularity in certain situations. For those of you who are interested in cosmology, the Starobinsky potential satisfies it, which is one of the best astrophysical constraints for the inflation that satisfies this particular condition on the scalar field with the potential. And then accordingly, incorporating fermionic and gauge fields are future prospects of this project. But right now, as I talk, I am right now calculating it for the electromagnetism, Bianchi IX coupled to electromagnetism, and it is showing that it might also be extended through it. Of course, the ideal case is to prove for the inhomogeneous non-isotropic metric of general relativity. There is no general statement as of now to make, but at least it's a crucial counterexample to challenge the conventional wisdom that the classical physics break down at the singularity. And these are the references which you might find helpful. And thank you.
Thank you, Rishabh. Let's thank the speaker for this very nice talk. Very good. So we will open the session to discussion. Again, I suggest that whoever is so inclined to turn on their cameras. And let me ask, yes, so do we have any questions from the audience?